Hey everyone, Mr. Fransky here, coming at you with 9.3a. This is the first time we're going to talk about really error with power series. So it's going to be a little intro today. We're going to talk about geometric series, and then when I'm back, we'll talk a little bit more about how to do this with Taylor series in general. So start with a little warm-up here, and if you want to give this a shot yourself, I think you should. Just want to give the first few terms, the general term from the Maclaurin series. Remember, Maclaurin means that we're centered at x equals 0. So centered at x equals 0 for each of these functions. Now, I would say try to do it by memory. The ones that AP requires you to know are on that yellow card. So you have to know sine, you have to know e to the x, and you have to know cosine. These guys down here are also ones that we added to our notes last week. And I think you should know how to do. They're not too bad. And then the other one we had was natural log of 1 plus x. But if you want to pause the video and see if you can remember at least for sine and e to the x, and see if you can get these other using those building blocks as well. See if you can give it a shot, and we'll come back together and do them together. All right, so let's see what you guys came up with. Remember that if you don't remember the Taylor series for these, that you can always just put it into the Maclaurin series. F of 0 plus f prime of 0x plus f double prime of 0x squared over 2 factorial plus f triple prime of 0x cubed over 3 factorial. And then you can just keep doing that for as many terms as you need. But these are ones that you should kind of have in your random access memory ready to go. So let's take a look at them. So sine x we should know at this point is all the odds. So it's x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. That keeps going, and the general term from n equals 0 to infinity, negative 1 to the nth power. That'll start on a positive because it's negative 1 to the 0, and then it'll be times x to the 2n plus 1. That'll get you all the odd numbers starting with positive 1 divided by parentheses 2n plus 1 factorial. That'll just give you the odd exponent and the odd factorial underneath. So then sine x squared, all we do is throw x squared in where all of those x's are. So instead of writing x here and here and here, what we're going to do is we're going to replace these guys with x squareds. Okay? So what we're going to have instead, this will be x squared minus x squared cubed, oh goodness, over 3 factorial plus x squared to the 5th over 5 factorial minus x squared to the 7th over 7 factorial, etc., etc. Could rewrite that as x squared minus, this would be x to the 6th over 3 factorial, and then it looks like it would be plus x to the 10th over 5 factorial, and then minus x to the 14th over 7 factorial. So it looks like we're going up by 4 in those powers every time, which makes sense because we're doing odd powers, and then we're multiplying them each by 2. But if we put that into a general term, you can just do this. I think this is the easiest way to do it. Negative 1 to the n, x squared to the 2n plus 1, divided by 2n plus 1 factorial. Now you could distribute this 2 to be 4n plus 2, but in my opinion, why not just leave it that way? Because I think that's the easiest. So remember, the cool thing about this is if you actually use enough terms, it'll approximate sine of any value, because we saw that this converges for all real numbers. That radius of convergence is infinity, which is kind of cool. All right, let's check the next one out. E to the x. E to the x we know is 1 plus x squared over 2 factorial plus x cubed over 3 factorial. Really easy to come up with a general term for this one. N equals 0 to infinity, x to the nth power over n factorial, and that's okay because 0 factorial is 1. So our first term will be 1 over 1, which is 1, and then we'll have x to the first over 1 as well because 1 factorial is also 1. Now here, once again, all we're going to do is replace all those x's with a negative x squared. So we're going to have 1 plus, I'll write this in parentheses, negative x squared plus negative x squared squared over 2 factorial plus negative x squared cubed over 3 factorial, and that'll keep going. Write a general term for that. Well, let's write this out a little prettier. So we have 1 minus x squared. This one would be positive x to the 4th over 2 factorial, and then we would have minus x to the 6th over 3 factorial, and that'll keep going. So we could actually write this as an alternating series. In fact, I think that's how I'm going to do it. So we go n0 to infinity, negative 1 to the nth power, because we start on a positive term, and then it would be x to the, looks like the 2n, so x to the 2n divided by n factorial. So you kind of got to play with that sigma notation a little bit until you're comfortable using it. But here we see we just have all even powers. You could also have done this as just negative x squared to the n over n factorial from 0 to infinity. All I did here was pull out the negative 1 to the n and also put the 2 and the n together. That's all I did for this guy. All right. Tangent inverse. So tangent inverse, remember, that's related to 1 over 1 plus x squared. So you might just remember this one. It looks a lot like sine, but just without factorial. So it's x minus x cubed over 3 plus x to the 5th over 5 plus, minus x to the 7th over 7. Can't write today. X to the 7th over 7, and that will keep going. And that's just the sum from n equals, let's start it at 0, I suppose, to infinity. It'll just be negative 1 to the n because it alternates, and then x to the 2n plus 1 to get all those odds divided by 2n plus 1. No factorial on the tangent inverse because this comes from the geometric. This is 1 minus x squared plus x to the 4th minus x to the 6th. And then when we anti-derive both of these sides, we get tangent inverse, and then we get x, and then minus x cubed over 3, x to the 5th over 5. So this is only good for absolute x less than 1. X tan x then, tan inverse, excuse me, we'll just add a power to all of these. So we'll have x squared minus x to the 4th over 3 plus x to the 6th over 5 minus x to the 8th over 7. Looks like that is sum from n equals, let's just go from 0 again, and we'll just add 1 to that power. So 0 to infinity, negative 1 to the n, x to the, this time will be 2n plus 2 divided by 2n plus 1. So we still have all the odd numbers on the bottom, but on the top we're getting the even numbers, and we're starting it at 2n plus 2, so we get, the first term is 2, and then we get 4, and then 6, and 8, that'll keep going up. Now the antiderivative of tan inverse, so I have to look at this guy up here, and I just antiderive it. So we're going to antiderive this side, so we'd have x squared over 2, minus, it would be x to the 4th over 4 times 3, plus x to the 6th over 6 times 5, minus x to the 8th over 8 times 7. Now, the general term for this one might be a little weird. Let's see here. So we sum from n equals, start at 0 again, to infinity. This time we need all the even exponents. So it'll be x to the 2n plus 2. So we have those evens again. So it's very similar to this guy. So it'll be x, negative 1 to the n, to alternate, x to the 2n plus 2, whoop, divided by, let's see here. So there's technically a 1 here. That's going to be important, I think. So it's going to be n plus 1 times n plus 2. I think that's right. So we have n plus 1. Oh, is that wrong? Let's see here. We need the odds, and then we need the odds plus 1. That's not quite right. So we'll have 2n plus 1, because that'll get us all the odd numbers. So that gets us the 1, the 3, the 5, the 7. And that'll be multiplied by 2n plus 2. That'll work better. Wow, that one was kind of tricky. And the reason for that is because we upped this power, and then when it comes to the front as a derivative, it would have to cancel out with this guy on the bottom. Huh, that's a cool one. All right, so let's get to the matter at hand. So this is great that if we add up forever and ever and ever, it's going to be true at least for a little interval around the center. But the question is, if we stop a series at any point, so if I stop this tangent one like here, and I want to approximate tan inverse of like 0.5, which is fine because 0.5 is within my little radius, I could plug in 0.5 here, here, and here, but that's not going to be exactly tan inverse of 0.5. It might be close, and of course we've talked about this. If I want to get closer, I can use more terms, but the question is, exactly how close am I? So what we're kind of driving towards is how many terms would I have to use to get like within 0.01 or 0.001? Like how far do I have to go to make sure I'm close enough? And the answer is, well, the more terms you use, the better. And what we've seen on Desmos is that e to the x, sine x, and cosine x converge for every x if you use the entire series. But what if you stop? So we've seen this in Desmos, so we can take a quick so if I go over to Desmos here, I've got it ready to go. So we've seen that with like e to the x. With e to the x, the more terms you use, the better and better it gets. Even if we zoom out here, the more terms I use, it'll get better and better and better. It's even getting better on this side. We can't see anymore because it's so close. But if you go down, like right, we started not great, and then as you use more and more terms, forever it gets better and better. And that's true with sine as well, right? We've seen this with sine, that the more terms you use, the better and better it gets. But if we think about this in terms of stopping, like what is that error value? So if you actually zoom in on some of these a little bit, You say, okay, so right now, like our error, the thing when I talk about error, I'm talking about the distance basically from the actual function to what you're using to approximate. So how good is that like for 1.5? Well, right now, it's not great. As I increase one term in, even one term in is pretty good, if I can keep it there. Two terms in, we see that you can't even notice the difference anymore. Oh, come on. Okay, so one term in, it's pretty good. Two terms in, I can barely notice the difference, and by the time I'm at 3 over here, there's still some error, but at that point it's good because it's closer to the center. So as I increase this, at this point we can't tell the difference between the curves anymore already when I'm at 16. But, and e to the x, kind of the same idea. If I zoom in, right now, pretty big error for these terms, but as I increase really quickly, it gets kind of, that distance between the red line and the blue line just goes away very fast. Okay, and we'll talk about kind of this Taylor idea another day, but today what I want to talk about is just looking at a geometric. We'll kind of do it the same way we would before. So if we think about a geometric series, where are they good and what's going to happen if I stop? So let's first think about what we have for a geometric series, something we've looked at before. So we look at 1 over 1 minus x. Guess we're using red now. That's going to be our first term, 1, and then our r here is positive x, so it'll be plus x squared plus x cubed, and that's going to keep going. And so this is actually equal to the series from n equals 0 to infinity, just x to the nth power. And the question is, all right, what if we stop like right here? Well, there's something really interesting with a geometric series. So as long as we're between, our absolute x is less than 1, in other words, our interval of convergence, -1 less than x less than 1, if I stop here, one thing to think about is what is true of the rest of the series. So if I stop at x squared, if I'm trying to approximate this for a value like 0.5, I know 1 over 1 minus 0.5, that's 2, right? Because 1 over a half, then 1 minus 0.5 is a half, 1 over a half is 2. So this value is 2. If I plug 0.5 in here, 1 plus 0.5 plus 0.25 is not quite 2. It's 1.75, right? It's getting close, but it's not there. So the question is, what is the rest of this worth? Let's think about what that would be. It'd be x cubed plus x to the fourth, plus x to the fifth, plus x to the sixth. This is my error, right? This is the amount that I'm off, okay? So if I'm using 0.5, the actual error will be 0.5 cubed plus 0.5 to the fourth plus 0.5 to the fifth plus 0.5 to the sixth, and forever and ever. What have I really created here? What is this series? Well, it's geometric, right? What's my first term? It's x cubed. That's my first term. And what is my ratio? Well, it's still x. I'm just multiplying by x every time. So the actual error, I can actually compute it. So if I use the first 3 terms to approximate 1 over 1 minus x, the error will be x cubed divided by 1 minus x. This is exactly what the error will be because it's the rest of the series, right? I've used 3 terms. I have a bunch of terms left over, an infinite number of terms left over. But we know as long as my absolute x is less than 1, this will be the exact error. It'll be the next term divided by 1 minus r. Okay, so to wrap our heads around that a little bit, I want to actually fill out a table with this. So we're going to think if we use n terms, so if it's 2 terms or 3 terms or 4 terms or 5 terms, whatever that number of terms is, what is the error going to be? Well, it's going to be the rest, right? So we go 1 plus x squared plus, and then we eventually get to x to the n, and let's say that's where we decide to stop. The rest of it is going to be x to the n plus 1 plus x to the n plus 2 plus, and this is going to go on forever. And the sum of all of that should be x to the n plus 1 divided by 1 minus x. Now, my question here of what does the error depend on is a couple of things. For one, it depends on how many terms we use. So the number of terms, which in this case is my n. So how many terms have I used? Because that's going to make my error smaller. Because if there are fewer terms to add up here, I'm going to have a smaller number. The other thing is the distance from the center. Because as we saw with e to the x and sine as well, if I'm closer to the center, then I'm going have a more accurate approximation of the series. So if I go back to my Desmos graph here, I have one here as well for our 1 over 1 minus x. Okay, we've seen this before. We looked at a couple different degrees, and what I'm going to do now is I'm going to look at this in terms of the error. So we're going to focus a lot on the value -0.75. So that's right here. So initially we've got a pretty big error here. You could approximate it. Looks like we're up here. This is maybe like 0.6-ish, and down here we're at like, I don't know, 0.25. So we have an error there of like 0.35, something like that. And as we increase, if we go up 1, And get that to exactly 2. There we go. Now we see we've got a smaller error. We only go from like 0.6 up to like 0.7, 0.75. So now we're at like an error of 0.15. Now we increase a little bit more. It's getting closer and closer. So by the time I get to like 7 here, we see at 0.75, very small error. The further I go, the better and better it'll get. By now, at 0.75, we can't even see the error. We'll zoom in a little bit more in a second. But notice if we had used a value closer to 0, if we'd use a value closer to 0, like right here, already our error is small. And then as we increase the number of terms, very quickly, it's already imperceptible, right? I mean, it's very, very small. So the distance you are from the center, and also the number of terms that you use, which is what changes the shape of this function, those are kind of the two things that will influence how much error you have. So what we're going to do, like I said, is we're going to focus on this value of negative 0.75. We're actually going to fill out a chart to be able to see what that is. So our hypothesis is this should be exactly the error. Okay, this should be exactly the error for any approximation of 1 over 1 minus x, as long as our absolute value of x is less than 1. So let's take a look at this. So we're going to use this. We're going to use a polynomial that stops at the nth term to approximate the value of 1 over 1 minus x for x equals negative 3/4. So we're going to say we're assuming x is negative 3/4. That's definitely within our bounds, right? Absolute x has to be less than 1. So we're between negative 1 and 1 here. And what we're going to do is we're going to increase the n, and we're going to see what happens to our error. Okay. Now this is something you're going to see a lot over the next couple of weeks. All I'm doing here is I'm saying what is the difference between the polynomial value and the function value. Okay. So first let's actually calculate the function value at negative 3/4. So if I do 1 divided by 1 minus negative 3/4, that's 1 over 1 plus 3/4. That's 7/4, that's 4/7 overall. You can do a little bit more algebra on that if you want to, but 4/7, I have that calculated out, is 0.57428. So I was pretty close when I was guessing that that was about 0.6. Okay, so 0.57428. So that is my target. Okay, I'm trying to approximate that value by using this series, and I'm going to use more and more terms, and we're going to see what happens with these values of the polynomial as we're getting closer to this value. We should be getting closer with the more terms we use. And we're actually going to calculate here the difference between our value and the actual function value. So if you have a calculator and you want to play along, you can. If you get bored of me filling out tables after a little while, you can skip through this. But I want you to see that it does work. The formula, this idea that we have, this hypothesis that we have, should work every time. And so let's see what happens. So we're going to go up to 2, 3, 4. We're going to go up to the 5th degree polynomial. So what I'm thinking here is, like, at this point, I just have a function of 1. Now I have 1 plus x. Then I have 1 plus x squared. So I'm increasing n. I'm going one more term further out each time. So at this point, this is going to be my term of just x. And that is negative 3/4. So the polynomial value at this point then, 1 plus x, I'm going to be adding as we go down here. So 1 minus 3/4 is 1/4, or 0.25. Okay, so 0.25 is not really that close to 0.57. So right now I'm not doing real well, but let's see what happens now. So my next term is going to be x squared, and I'm actually going to go to decimals here. In fact, I should have done this as a decimal. This is going to be negative 0.75. The x squared, so what I'm doing here now is negative 0.75 squared. That term is 9/16 or 0.5625. So if I add all three of these together now, 1 plus x squared, at this point I am at 0.8125. Okay, so on Desmos, as we saw, we were kind of going up and down around the value. So if I go back to that, I think it's worth it. Go back to our Desmos screen here. At this point, what I'm at is I'm at a degree 3 polynomial. I think I was actually only at 2. So I was at a square. So we see is right now our distance between the function, our actual value is down here. We're down at, back to my value here, let's take a look. We're actually at 0.8125. So 0.8125, we should be above it. Let's see here, what did I do? Oh, come on. That's what I want. So let's see here. So we're only at a squared. That's what happened, is I went too far. Come on, give me 2. I know you can do it. There we go. Okay, oh, go away. Goodbye. So at this point, if I can get it to square, keeps wanting to move on me. Stay. Man, I'm having all kinds of trouble with this. There we go. So at this point, we're at 0.8 right up here. Okay, so our value is too high. Now if we go to 3, our value should be too low. Okay, I'm just going to go back to my table here. So if I go to 3, so now I'm going to have 1 plus x cubed. And where that's going to put us is our x cubed term is going to be a negative value. And that value is negative 0.4218. And if we subtract that off, right now we're at a polynomial value of 0.3906. So you can see we start too high, because 0.57 is our target. We start too high, then we go too low, then we go too high, but we're closer. Then we go too low, but we're still closer. So if we calculate this error every time, so the difference of 1 from this value is 0.4285. I just did this by subtracting. What I'm doing here is I'm subtracting 0.57428 from 1. And if it's negative, I'm just going to make it positive. That's why I have the absolute there, because I'm just trying to find the error, the difference between them. 0.25, the distance away from 0.57 is 0.3214. And 0.8125 from here, that is a distance of 0.241. This guy is a distance away of 0.18. And you can see our error is getting better as we go, which we expect, right? We know the more terms we use, the better it should be. Now, the amazing thing is that this is exactly this value. So if I do here, if at this point I do the rest of the series, which is going to start at x. So this would be, our first term would be negative 0.75 divided by 1 minus negative 0.75. If you calculate that out, it gives you exactly 0.4285. The next one I'm going to do, it's going to be our term, negative 0.75 squared divided by 1 minus negative 0.75, because our ratio never changes, right? We keep multiplying by negative 0.75 every time. What happens is we change our starting value, right? So at this point, we've done 1 plus x. The rest of it is going to start at x squared. And that value gives you exactly 0.3214. So the point is, we're going to do an example next where we don't have to do all of this work to find out what the error is. All we have to do is use this little term right here. Okay? So the next one would be negative 0.75 cubed divided by 1 minus negative 0.75. And that ends up giving you exactly 0.241. So we're lining up on all these. The next one will be 0.18. Okay, and if you're interested, the next term, if you want to fill out this table, you can. But the next term, x to the 4th, gives you 0.3164. If we add that on, it gives us 0.707. So once again, you see we're getting closer. We're at 0.81, then we went below. Now we're at 0.707, which is closer than 0.81. That gets us an error of 0.135. And this one also turns out to be 0.135. Okay, the hypothesis works the whole time through, because that would be starting at the 5th term and going off to infinity. And in the 5th term, we have negative 0.2373, and that is an error of 0.1017. Oop, I messed something up. Nope, sorry. The polynomial value is 0.469, and the error value is 0.1017. So once again, we see we're getting closer, and that will work out. So as we see, and this is we know this, like as we use more terms, we get better, and that error gets smaller and smaller and smaller, and eventually will hopefully turn into 0. So what was that punchline again? Because I feel like when we do these tables, like things get very muddled, and it's like, what the heck are we showing? So the point is, when using a finite geometric series to approximate the sum of an infinite series, the exact error is the remainder of the series. So if we want to use a over 1 minus r, any a and any 1 minus r. And in this case, we're most interested when there are x's involved. But we know that that is equal to a plus ar squared plus blah, 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 all the way off to infinity. So if we approximate this with a plus ar squared plus blah, 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 and eventually we stop at ar to the, let's say, n minus 1, because we started at 0 here, then the error is always just the rest of it. So it's going to be the first term, which is ar to the n, divided by 1 minus r. Okay, that's our error term. We're always going to go one further, and then our ratio will not change. So let's look at what that looks like in an example. So if you use the fourth degree series to approximate 1 over 1 minus 2x, what will be the error in terms of x? What is the error for f of 1/8? And will this work for f of negative 3/4? So let's kind of see what this is all about. So first, let's figure out what the fourth degree series is to approximate this. Well, I know that this, as a series, our first term is 1. Our next term is going to be, so our r here is 2x. r is 2x. So it's going to be 1 plus 2x, and then plus in parentheses 2x squared, and then plus 2x cubed, plus 2x to the fourth, and then forever and ever and ever that goes on. So we don't want to stop at the fourth degree, though. So there we are. Okay, so that's our fourth degree. Okay, some might call that P4, because it's the fourth degree polynomial for this, this function, this 1 over 1 minus 2x. So the error in terms of x is going to start at the next term. Well, what's the next term? It's 2x to the fifth. So the error will be the next term, which is 2x to the fifth power, divided by still 1 minus 2x. That is the error in terms of x. So I say, what is the error for f of 1/8? So this is saying if we use the fourth degree to approximate this, that'd be 1 plus 2 times 1/8 plus, it'd be 2 times 1/8 squared, plus 2 times 1/8 cubed plus 2 times 1/8 to the fourth. If we approximate it using this, it's not going to be perfect, but without calculating anything, I know the error will be 2 times 1/8 to the fifth power, right? That's the next power, divided by 1 minus 2 times 1/8. Okay, I'm going to grab my calculator, and I'm going to do 2 times 1/8, which is 1/4, so 0.25 to the fifth power. 0.25 to the fifth power gives me a small number, divided by, let's do this all at once. 1 minus 2 times 1/8, parentheses, 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 gives me 0.0013. Wow. So with only using up to the fourth degree, I have a tiny, tiny error. Now, you might show this to, like, your boss, because it wants this, approximation, and they say, nope, I need it to be below, like, a thousandth. So you could say, okay, I'm going to go one more term. And you could keep finding which error term is going to get you below that threshold. Kind of cool. So you'll see this in your homework tonight. So a preview on what's coming. Really, that's all you have to be able to do today. So this works great for geometric series, but once again, the question is, why is it that e to the x, sine x, and cosine x converge for all values of x? Because geometric series only converge for absolute r less than 1. And the question is there a formula to calculate error for the other Taylor series? And we'll do that when I get back. Remember, there's a quiz tomorrow. It doesn't have error on it at all. So this is new that will be quiz on later. But right now, all you have to know for 9.1 and 9.2 is in the summary video that I'm going to post in just a few minutes here. So you'll have that online as well. And then your homework tonight is going to be dealing with the error of these geometric series. So you'll have some more complicated ones. But remember, it's just always the next term. And then you divide still by 1 minus r. That's kind of how you find error for geometric. I'm going to show you some cool things on Desmos right here, just kind of some zoom-ins on the one we were just looking at and see how close we can get it. But otherwise, if that's the end of it for you, then I love you guys. That's why I'm here, and have a great day. But let's take a look at some things that are going on with this error stuff in Desmos. So if we look at this, this function, which is still 1 over 1 minus x, and we look at how good we can get here, let's zoom in on that negative 0.75. So right here. So right now we've got a pretty good error. And if we keep going a little bit, we see that it's getting closer and closer and closer. So fifth degree is the furthest that we went in our table. So this was the error value from like about 0.5 to about 0.6. So we got to about 0.1. And if we keep increasing, you see it's going to get closer and closer and closer. They don't like me holding on there. Closer, 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 right? And eventually, it's going to be imperceptible. But if we zoom in a little further, check that out. We can now see that error in there. And still, look how small that error is now. But if we keep increasing, 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 it keeps doing that hula dance around that value. But if we zoom in a little more, you see we still have error there. Now, at this point, we're down to below 0.001. That error is so small. But if you keep going, it gets smaller and smaller. But once again, we can zoom in more. It'll never be perfect, right? Unless we use an infinite number of terms, which we can't do on Desmos, certainly, right? But closer you are to 0, the better the error is. And the more terms you use, the better that approximation will get. All right, that's it. That's all I got for you today. I love you guys. That's why I'm here. Have an excellent day. There is a summary video for the quiz tomorrow for 9-1 and 9-2 if you would like to watch that. Have a good one.